If you say, what is the f of 4, you will get, so instead of a particular point from the xy domain, and that will map onto a one-dimensional range z. So that one maps, let's say here, as a z0 using function f of xy. So the example for something like that would be, let's say, f of xy is x squared minus 3xy. So it's just a function that has a whole bunch of these x's and y's on a pile. You can have ln y, you can have sine squared of x times y, anything that, you know, crosses your mind in any way you want to put it together. And then the question is if it's useful, obviously, to model anything that we have. So now if you want to compute, let's say, f of 1, 3, you will replace all x's with 1 and all y's with 3 and just compute. So you have 1 squared minus 3 times 1 times 3 is 1 minus 9, which is negative 8. So you see that the input, your input was 1, 3, produced the output z equals negative 8. Now this is very important to understand because this is how we describe three-dimensional surfaces. What you have on the floor is the xy coordinate plane, which has infinitely many xy points, and you can use them to find the location. If you take a 0, 0 in a corner of the classroom, as we agreed the day one, right? Take the 0, 0 in a corner and measure in feet, x-axis along the wall, y-axis along the wall with the board. You can find in feet, let's say, using the grid on the ceiling, you can find location on any one of your chairs as the coordinate system of x, y. Now, adding the height, right, will be the part of the function because, as you can see, this is not a flat surface now. Each one of you is, and me, right, creates a bump. Each chair creates the bump off of the surface of the floor. So, now these are the half ones. That's a 1 foot. So if I pick any location, right, you will go 2, 4, 6, 3, 5. Great. So 6, 5 location on x-axis, right? So you can find each 6, 5 as the input, right? So 6 in x and 5, no, it was 5 in x and 6 in y. So 5 in x, 6 in y for the location. And that would be the input, right? Now there has to be some kind of a function that will calculate the height. So when you have some kind of a surface, three-dimensional surface on top, this could be a hill outside, it could be the surface of the printer over there, doesn't matter, right? It's going to be described by one of these equations. Every single height, y, corresponds to the calculation which you got when you calculate xy variable from the floor in that function that will give you the z elevation. So you can calculate elevation of any point if you know, obviously, what the function is. And it's done simply by plugging numbers in. So you see that the function works exactly the same as all of the functions you know from your Calculus 1 and before, except now you just have to be careful to plug x for x and y for y. And we're going to have a little bit more, it will be trickier to find the domain, because now domain is not just the interval like it used to be in R2. Domain now could be a blob, could be a circle, could be a half plane, right? All of the numbers on one side and so on. So the domain is trickier to find, but the concept of the way, in which the function works is exactly the same, except now you have 2 input values instead of only 1. So function in R3, function is mapping two-dimensional points into one-dimensional value. So you have two in domain, one in a range. It's a 3D. It's a 3D concept. So now we would like to talk about the domain of these functions. We have these key important words: the word rule, the word domain, the word range, and the word unique, right? Those are the key words in this definition, which everyone will have to know for exam 2. So this is me telling you the question on exam 2 for 4 points. 4 points on exam 2, this red statement here, written that way. I mean, with better handwriting, obviously, right? Do what? What is the definition of the multivariable function? That's the question. And your answer is the red stuff. For 4 points. 4 points for 4 words. If you lose any of these words, you break the definition of a function and the whole definition of a relation. Circle has a formula. Formula is a rule. Circle has domain, circle has range. Yeah, but it's not a function because the vertical line test cuts it twice, and a sphere, right? It's not a function because the z-axis will cut twice through the ball. So it's not a function. So in order for function definition to work, all 4 words must be present. Now we see that the domain over here, right, is going to be a 2-dimensional domain. So now we need to discuss domain. The range is, again, interval, right, of between 2 numbers on z or infinities or so. So domain is the tricky one. So all of the rules which you learned in Calculus 1 or pre-calculus for domain still hold, except now you have to worry about working those rules in 3D. For instance, you had a theorem which you memorized, and that theorem said that domain of polynomials is all real numbers, right? So if you have the equivalent of a polynomial in 3D, well, I mean in the 2D input for the 3D function, you are going to have the same rule. The rules don't change because you added extra dimensions. Calculations change, while the rules stay the same. So, if you take a look at y equals x squared plus 3x plus 7, and you say domain is all real numbers, that's your pre-calculus talking, and you're right. Now, you have a z equals 3x squared y minus x plus 4y squared. Well, this is also polynomial-like, right? This is the equivalent of a polynomial for the three-dimensional R3 space. And its domain, it's going to be all points in R2, right? Because our domain is x comma y. So let's go do it this way. All xy points in R2. So that's my comparison between the two worlds, the world of R2 on the left and the world R3 on the right. Another example. So let's just strike this vertical line over here and then make this as a chart where you have the left and the right and left and right. So now in the world on the left, you know that if you have a function y equals 3 over x plus 7, you know that your domain will be all numbers except x is not allowed to be -7. Because if f is -7, you are going to run into issue of 0 in denominator. And we don't like that. So a very basic problem. Can you have something like this in R3? Of course. Z equals, I don't know, 10 divided by 2xy minus 6. 2xy minus 6. So you immediately say 2xy minus 6 is not allowed to be 0. And go ahead, solve it. So if you are solving this now, you will have 2xy is not allowed to be 6. Xy is not allowed to be 3. And now you can write it as a formula where y is not allowed to be 3 over x. So now what does this mean? This means that the function you have, the multivariable function you have, will have as a domain all numbers available to it to compute except the numbers along this function in the xy domain. So if you are to draw a domain here, you will draw this function as we all know that, that's pretty much what it is. And I'm going to actually replace these with red lines. There we go. So you are allowed to pick any point that it's not on these red lines, and you can compute. So, would our problem up there work for 0, 0? The answer is yes. 0, 0 is not on these red lines. So if I plug in 0, 0 in z, it is going to work. Let's test it. Plug in 0, 0, it kills the first term. It's 10 over -6, so -5/3. Excellent. It works. 0, 0 works. Would 1, 1 work? Of course it would work because 1, 1 is not on the red line. Plug in 1, 1, you get 10 over 2 minus 6 is -4. Perfect. 10 over -4. You can reduce it and you have the answer. Now, can you pick 1, 3? No. Point 1, 3 is on the red line. And the point 1, 3 will give you a 0 in denominator. If x is equal to 1 and y is equal to 3, 2 times 1 times 3 is 6. 6 minus 6 is 0. You have 10 over 0. No bueno, right? So when you are solving the domain for 3D functions, you keep the same rules and the same logic as when you are solving them for your two-dimensional functions. You always keep asking yourself, so now the new feature is that you can have a function telling you what you are allowed or not allowed to use. So in this case, this is the rational rational function equivalent. We solved it the same way. We figure out what points we must exclude. We exclude those points, and we say domain are all points except on the line y equals 3 over x. Or you can say domain is y cannot be 3 over x. So either way you want to write. So those are the two ways. Just don't mix the two ways right together. Don't say all points except y cannot be -3, because in that case double negation there, and being that the language is not set up, English is not set up for double negations, you can get in trouble with math. It took me a long time when I moved in to filter the double negations, because my language is based on double negations and so on. We use it a lot, but English doesn't have it, so it's very difficult to. It's very easy to make the mistake of doubling up on negation to provide the answer. So your answer is either all points xy except y equals 3 over x, or you will say exclude, well, no, you will say or just y cannot be 3 over x. It's understood that all other points work. You are just stating. So either one of these two. But you cannot put this as crossed out. All right, so next example, just to show again that we are working with the same ideas. Next example would be in R2, you had y equals square root of 3 minus x, right? That was what we call a radical function. To find a domain, you know that you are supposed to set the argument larger or equal than 0, because if the numbers under the root are positive or 0, the answer would be real. If they're negative, the answers are imaginary, and we have to take them out from the calculation from the square root because it's not real. So we would say 3 minus x needs to be larger or equal to 0. You move x to the other side, you get 3 larger or equal than x. And then if Tom is taller than Mark, Mark is shorter than Tom, right? You flip it around. And this is your domain, right? So for the domain, you are allowed to pick values that are 3 or less. That's it. So let's say you pick 2. Would 2 work? Well, of course it would, because 3 minus 2 is 1, square root of 1 is 1, we're all happy. Do you want to pick negative 1? Sure. 3 minus negative 1 is 3 plus 1, which is 4, square root of 4 is 2. So it works. Can you plug in 10? No, because 3 minus 10 is negative 7. But see, 10 is not smaller than 3, so we know it's not in the domain. So what is your third-dimensional equivalent? Well, let's say you have z equals square root of, I don't know, 2 plus x minus y. Literally, just put anything. It's the same rule. Whatever is under radical must give a non-negative value. So you will write immediately 2 plus x minus y must be bigger or equal than 0. Well, that's nice. All you need to do is to ship y on the other side, and you already have the solution. So 2 plus x greater or equal than y, which means y is smaller than equal than x plus 2. This is your domain. All values that would satisfy this inequality. So you can draw this, and you can shade the region that it's okay to use, and obviously not shade the one that you can't. So x plus 2, let's say 1, 2, and it's a 45-degree line, and it's a solid line because it's equal, right? So we have a line like this, and now I need to shade above or below. You can just quickly test 0, 0 to see if it works or not, and then shade over it or away from it. So 0, 0 will give me that 0 is less than 2. 0 less than 2 is good, so we know we need to shade below. So your domain is in the shaded region. Any point that you pick from the shaded region would work in our equation. If you pick anything that is outside of the shaded region, it will not work. This point here is negative 2, 2. That point would not work. Negative 2, 2 would not work. It's not in the shaded region. Now plug it in and see. You have 2 minus another 2. Well, that's 2 minus 4, which is negative 2, square root of negative 2. Well, we're not happy campers there in terms of real numbers. Getting a region of, interval of numbers, now you're getting a region in 2D space that it's okay or that it's not okay. I can do one more example, and then I think we beat this to death. let's say log function, whatever. So y equals ln of 4 minus x, x minus, how about x plus 4? Because we had earlier 3 minus x, so let's do x plus 4 now. Now for ln has a vertical asymptote at 0, so argument of ln cannot be 0 and cannot be negative. So you take the argument to see that x is bigger than negative 4. So any value, that would be your domain in R2. So any value you pick, right, where x is bigger than negative 4, you are okay to work, right? Now let's say you have z equals ln of what? xy plus 3x. Literally, just put whatever. No one cares, right? Just anything. Put anything. The rule has to be the same as in R2, which is whatever your argument is over here gets the bigger than 0 treatment. So xy plus 3x needs to be larger than 0, because all of this here must produce positive number. Otherwise, ln will give you a complex value. The imaginary, right? So there you go. This is already your solution. Question is, do you want to make this prettier? Maybe you want to. So you will factor out x. You have your y plus 3 larger than 0. And then you realize that if you divide both sides by x, right? And you know x can't be 0, because if you put x equals 0, then you have ln of 0, and that's where the vertical asymptote is. So x equals 0 is already excluded, like the whole line, x equals 0 is excluded from your calculation. So if you divide, you just get y plus 3 larger than 0, and you have y larger equal. Why do I have equal? Where did the equal come from? Y larger than negative 3. So this is a two-part domain. Y larger than negative 3 and x cannot be 0 are both part of the domain. So both of these need to be true in order for you to have the domain. So if you are to draw this, y larger than negative 3, let's say this is negative 3, and we have to use dashed line at negative 3 because it's not included. And you get to shade everything above, but you have to exclude the line. So here's me with the red excluding x is not supposed to be 0, but the domain is everywhere around it. So I don't get to shade on x equals 0. So now let's say you pick y equals to 10, right? You can pick y equals to 10 and x equals anything other than 0. So can you pick 1, 10? Yes. 2, 10? Yes. 10, 10? Yes. 0, 10? No. Because 0, 10 is on the y-axis, which is x equals 0. And we see that we cannot have to this idea, but the same rules you guys had for R2 are carried here. They're carried to the 5th dimension and the 17th dimension. All the same rules, except you have a lot more variables to consider, right? But we are staying here, 2 input variables to create a 3D function to describe the space and surfaces around us. So that's what we have in terms of domain. And domain is going to be one of the questions on the exam too. So one of these examples with a different function, so either a polynomial, where you just say everything is in the domain, or something with a root, or rational, or something like that. So this is definitely one of the questions. Because again, your function definition, that's 4 points, right? And then the domain, it's another 4 points, and then maybe I can say like what's 13 times 7 for another 2 points, and that is the 10-point question. Would that be cool? All right, we're all good with 13 times 7? It's not too high? Okay. It's like, yeah, I got my trusty calculator over here. 13 times 7. 10 times 7 is 70. 3 times 7 is 21. 70 plus 21, 91. You need a calculator. Just multiply the units. Each number is divided into hundreds plus tens plus ones. Multiply each one of them. It's a single-digit multiplication, and just add them at the end. No need for calculator. Okay, the next part is, I believe, level curves, and we are done with the lecture. Yes. The next part is level curves, and level curves are just going to be your XY trace done at different elevations, which we call levels. So, level curves. Level curve has a constant elevation in respect to z axis. So we'll just say z equals z0. So if I am to draw, let's say, a ball over here, sitting in this three-dimensional x, y, z space, I can come up with level curves on this ball. So let's say the black line here is the equator. That's where the ball is the fattest, right? Because the ball is a single point on top and gets fatter, fatter, fatter. And the equator is where it's fattest, and then it goes again skinnier, 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 and then at the south pole is a single point, right? So if you are to take a sword and cut with these horizontal planes, each cut would reveal a circle as what we used to call trace in the xy plane, parallel to xy plane. But all of those planes are on the elevation z equals something. Now, we did talk about it when I told you that we cut the watermelon. I went yesterday to see if the price of watermelon dropped, and it's still $8. As soon as they dropped, you're getting a video with a watermelon cut. So it's for science, right? So when you do the side cuts over there, each one of these red lines is going to be on a different elevation. So let's say that this sphere has a radius of 5. So this elevation here would be z equals 0. Next elevation is z equals 1. Next one is at z equals 2. Then this one is z equals 3. This one over here is z equals 4. And finally, the top over here is z equals 5, which is just a point. So these level curves are actually going to be values for z. Now, we know that if the radius of the ball is 5, you are going to have x squared plus y squared plus z squared equals to 25 as an equation of the ball, of the sphere. And let's say this is something that it's radius 5 meters, 5 feet, whatever. So it's just, it's a ball. So now what happens is when you cut this with z equals 0, you come up with the equation for the circle for the black line, and that's the circle with radius 5, because this is where the ball is fattest, and the fattest part obviously will have the full radius, right? So z equals 0 removes z from the equation, and you just have x plus y equals 25, and that's the equator. But now you go and you cut with the plane z equals 1. That introduces to 24. Well, clearly the radius is smaller, right? Because you made a cut on top, right? So the red circle, the first red circle with the z equals 1, has the smaller radius than the black circle here, which had radius of 5. So square root of 24 is 2 root 6. That's less than 5. So this stuff over here is z equals 1. You can have a level curve with z equals to 2, so x squared plus y squared plus 2 squared is equal to 25. That's x squared plus y squared equals to 21. This is z equals to 2. The important part is that you are on this constant elevation of a z equals something. And that is important to us because we can create terrain maps. Terrain maps will tell you, if you know to read a map, it's a very useful skill, by the way, if you, once the satellite and GPS are down, if you don't know how to read the map, you're not going to have a good time finding anything. The map of a terrain is would look something like that. It's going to make it larger and just give you a few pointers that you might want to study further. So here we go with the map. So when you take the map, you are going to find a lot of these curvy lines, and those are your level curves. And when you have the colors will tell you what type of terrain you have. So if it's green, it's probably grass and forest and so on. If it's right, and it's a valley, so it's like lower, and then the more brown it gets, the higher the elevation. So the darkest brown should be the highest elevations on that map, if the map is done properly. You also have a scale on the map, which will tell you that 1 inch on a map is maybe 1 mile in the real life. So you can actually, figure out how far the things are. Now, the reason why this map is in Calculus 3 is because of these really, really curvy lines that are everywhere. These curvy lines mean that if you are to walk on the curved line, so pick anyone, pick this one. So if you are to walk along this curved line, the height at which you are on the outside is not changing at all. So if this curved line here is 300 feet above sea level, it's going to be 300 feet sea level as far as that line goes. You will always be on a same line. The higher you go, the ears start popping, because of the pressure of the air, right? There's less oxygen in have all these people that want to climb Mount Everest, right? And they say, yes, let's go. And then they get there and then they die because they never practiced it, right? You have to actually train before you go. Now, when you look at the map, these level curves on the right are far apart, and these over here are very close by. When the level curves are close by, it shows a very steep incline or decline. You cannot drive here. Military cannot drive here. No one can drive here because these level curves are so close that you have a very steep incline. Over here, right, it's not as steep. Now there is a nicer picture in the book which shows the way you cut. This is for electric potential in electrical engineering, but it's much easier if you think of this as termite nests. So electric potential function, But let's not worry about that. Let's take the object of termite nests. Termites tend to build these, right, in deserts and so on. If you ever watched any of the survival shows or whatever on the Discovery Channel before they became all about sharks and Nazis, they used to also have animal shows there. And you could learn about termites building the nests that look like this, right? Which is very useful because there's water and flood and it doesn't flood the insides and kills the little ones. So what you are expecting to see are the level curves on the bottom to be far apart and the level curves for this part, right, as you start slicing with equally spaced, let's say 1 inch, 1 inch, 1 inch, 1 inch, right? Cuts z equals 1, z equals 2, z equals 3, 4, 5, 6. You are expecting these circles to be very dense. So now when I reveal to the right, boom, look at that. So, not too much of an incline here, right? Not too much of an incline. Look at the level curves, far apart. A lot of incline over here, close by. So now if you translate that to a map, if you have a map, right, and you are about like looking for buried treasure, right? When you see this, well, you need to have gear, right? Because it's either gonna be going down, not fun. I mean, Spider-Man not a problem, but for you it's a problem. Or going up, it's also a problem. So close, level curves close, you have a very steep drop, level curves far away, you have a very shallow drop or now, as long as the curves are present, you always have some kind of elevation because the only way to get from one curve to another curve is to change the height because it's from z equals 1 to z equals 2. So if the curves are present, you must have elevation change. Now, how far apart they are, that's the only thing that tells you of how much elevation change is taking place. So what I want to take a look here is hopefully find some of the, oh, look at that, that's nice. Here are some throw-dimensional graph where the fourth dimension is represented with a color. So you can think of, I don't know, let's say this is an engine block in a car or something. The temperature would be the fourth dimension added to the mix to show hot, extremely hot parts and the cold parts in these areas. So you can actually interpret four-dimensional graphs on the 2D surfaces as well. Now I want to see, there they are. That's what I was looking for. So I'm looking for these problems. Where is my, oh, here, I think. There you go, with your book that it's $7,000. So level curves will appear on the exam and they will be in this format. You have a shape and you have to pick which level curve. Now I'm not going to give you a 6 and a 6. I'm going to give one shape and 4 choices. So it's a multiple choice question, and unlike MyMathLab, right, you will only have a chance to click once. I mean, circle one once, rather than MyMathLab, right? You click one, it says wrong, and then you go and change another one, and say yes, and you get a fantastic, and you feel good about yourself. So before we move on to the next lecture, because we are done with this one, right? Page 928, if you're following the books or something, or your local computers, I want you guys to take some time and talk to people sitting next to you, if you care, to match the 6 green, or whatever the hell this color is, it's green, right? Green to the orange, like which one belongs to which one. And so take some time, and I'm gonna shut off the stream because this is not on. Bye.